In this video, I will teach you how to identify and evaluate limits that are actually derivatives. If you appreciate the content, please give it a like. Back in Unit 2, we learned both the traditional and the alternate limit definition of the derivative. This is the traditional limit definition of a derivative, and this is the alternate limit definition. If you see a limit in either one of these formats, you can evaluate the limit by evaluating the equivalent derivative. For example, this limit matches the format of the traditional definition of a derivative. Comparing this limit to the definition of a derivative, we can see that f of x must be sine x, and the c value is pi over 2. So this limit is equivalent to f prime at c. So in this case, that's f prime at pi over 2. If you're curious why there's a 1 here instead of f at c, that's because f at c in this case would be sine of pi over 2. And guess what? Sine of pi over 2 is 1. Since this limit is equivalent to f prime at pi over 2, where f is the function sine x, we can evaluate this limit by taking the derivative of sine x and evaluating that at pi over 2. The derivative of sine x is cosine, and we can evaluate cosine at pi over 2. Cosine is the x value on the unit circle, and cosine at pi over 2 is 0. So that's a really easy way to evaluate this limit. Pause the video and try to evaluate this limit on your own. Comparing this limit to the traditional definition of a derivative, f of x must be 5 to the x power. In this case, it's a little bit tricky to spot the value of c because it's actually 0. This is 5 to the 0 plus h power, so the c value is 0. If you're curious why there's a 1 here instead of f at c, it's because if c is 0, then f at c would be 5 to the 0 power. And guess what? 5 to the 0 power is 1. We can evaluate this limit by evaluating f prime at 0, where f is 5 to the x power. Here's the memorized rule. The derivative of a to the x power is a to the x power times the natural log of a. So the derivative of 5 to the x power is 5 to the x power times the natural log of 5. This limit is equivalent to f prime at 0. So that's going to be 5 to the 0 power times the natural log of 5. 5 to the 0 power is 1. So this simplifies to the natural log of 5. And that's the value of this limit. This limit matches the format for the alternate definition of a derivative. Comparing the limit to the definition of a derivative, we can see that f of x is 2 to the x power. For the alternate definition of a derivative, it is easiest to spot the value of c right here, the limit as x approaches c. So in this case, the value of c is 3. If you're wondering where the 8 is coming from when you're expecting to see f at c, remember that f is 2 to the x power and c is 3. So f at c is 2 to the 3 power, and that's 8. We can evaluate this limit by evaluating f prime at 3, where f is 2 to the x power. Using the memorized derivative of a to the x power, the derivative of 2 to the x power is 2 to the x power times the natural log of 2. So f prime at 3 will be 2 to the 3rd power times natural log of 2. 2 to the third power is 8. So this can be written as 8 times the natural log of 2. You can write your answer in either form. Just to be thorough, here's one more form that you might see on a multiple choice question. We can use the properties of logarithms, which say that when you have a multiplier in the front, you could move that to the exponent if you wanted to. Later in the unit, we're going to learn something called L'Hopital's rule, which is another way of evaluating the same three limits we just did. I'm going to preview L'Hopital's rule for you today. L'Hopital's rule says that if f and g are both continuous, and if direct substitution yields 0 over 0 for f and g, then the original limit is equivalent to the limit of f prime over g prime. In other words, you can take the derivative of the numerator and the denominator without changing the value of the limit. Before we can use L'Hopital's rule, we must show that direct substitution gives 0 over 0. So notice if we plug in 0 for h, we have the sine of pi over 2, which is 1. That leaves 1 minus 1, which is 0. So this little step I'm doing right now is mandatory. You need to put an arrow, 0, and of course if we plug in 0 for h, that's 0 as well. So you have to show that too. Arrow 0, arrow 0. I'm using arrows like this because we are not allowed to write this down. This is boo, bad notation. You cannot divide by 0, so you can never write down 0 over 0 as a fraction. That's wrong. So just put arrows like this. Now we can do L'Hopital's rule. According to L'Hopital's rule, we can now take the derivative of the numerator and the denominator without changing the limit. Let's start with the denominator. Since this is an h, we are taking the derivative with respect to h. So the derivative of h is 1. So you can see why L'Hopital's rule can sort of simplify the limit. Now, the derivative of the numerator. The derivative of sine is cosine. We are doing the chain rule, so we leave the inner part alone, but then we multiply by the derivative of the inner part. Going term by term, the derivative of a constant is 0, and the derivative of h is 1. So we'd be multiplying by 1, which we don't need to show. Also, moving on to the next term, it's another constant, so the derivative is 0. So that's it. So what is the value of this limit? We can evaluate the rest by direct substitution. Plugging in 0 for h, we are left with the cosine of pi over 2. And that's 0. So that's the value of the limit. If you look back and compare this to how we did it the first time, you might notice that it's actually the exact same thing. Now let's do the second one. First, we must show that direct substitution yields 0 over 0. If we plug in 3 for x, that's 2 to the third power, that's 8. 8 minus 8 is 0. Of course, if we plug in 3 right here, 3 minus 3 is also 0. Showing this arrow 0, arrow 0 is mandatory. You have to do this before you proceed with L'Hopital's rule. According to L'Hopital's rule, we may now take the derivative of the numerator and the derivative of the denominator without changing the limit. The derivative of 2 to the x is 2 to the x times the natural log of 2. And then the derivative of 8 is 0, so we don't write anything. The derivative of x is 1. And the derivative of 3 is 0. So that's it. We can evaluate this limit by direct substitution. Plugging the 3 in for x gives us 2 to the third power times the natural log of 2. This is exactly what we got the first time. L'Hopital's rule one more time. Pause the video and try the last one for yourself. Direct substitution. If you plug in 0 for h, you get 5 to the 0 power, which is 1. 1 minus 1 is 0. If you plug in 0 for h in the denominator, you immediately get 0. Showing this arrow 0, arrow 0 is mandatory for L'Hopital's rule. Make sure you don't skip this step. Now, according to L'Hopital's rule, we can take the derivative of the numerator and the derivative of the denominator without changing the limit. The derivative of 5 to the h power is 5 to the h power times the natural log of 5. The derivative of 1 is 0, so that's it for the numerator. The derivative of h is 1. We can evaluate this limit by direct substitution. Plugging in 0 for h gives us 5 to the 0 power, which is 1. So we're not going to write that. That leaves the natural log of 5 for the final answer. Hey guys, don't forget to like and subscribe. But also, if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.